Okay, let's begin. Today is gonna be a it's gonna be wrap up. So short class in the sense that we only have two more circuits left. Late yesterday night, I realized that we're almost at the end of chapter 4. This is the fastest that I've ever gone in 321, and we're only at the end of week 7. We pretty much covered 90% of the material, actually more than 90% of the material. So what I did in the previous section was I we went over the two circuits that are left for today, and then I went over the labs, which was 6, 7, 8. Okay. How many of you have had lab 6 completed this week? Okay, so you got 1, 2, 3. Is your lab on a Wednesday, or was it a Monday, Tuesday? It was Tuesday. Lab 6 on a Tuesday. What did I do? Wait, so did you start a week early? Ah, okay, that makes sense. Okay. All right. 6, 7, and 8. All right, we'll look at that later. All right, so what we're going to talk about today is a register. Okay. A register is nothing but an array of flip-flops. It allows you to register or store some memory. Remember, we looked at D flip-flops last class, delay flip-flop, right? That delay flip-flop might seem like, okay, all it does is it sends an input to the output. What is the purpose? Well, here's the most important purpose. We use it to store data and forward it. Oh, sorry, never switched over. Let's switch over. Okay, so it stores data in memory, and it stores data, so it's known as a register. It stores data, so it's known as register that stores memory. And there are two ways to either send the data in or receive the data out from this register. Okay, we can do it in a serial fashion, or we can do it in a parallel fashion. So I'll explain what it means. Let's say you have a 4-bit register or 4-bit system, right? So if it's a 4-bit system, you need 4 wires, right? 4 wires, 4 circuits, everything is 4 times. If you want an 8-bit system, you need 8 wires, 8 circuits, 8 systems, everything is replicated 8 times. So when we first, the world's first processor going way back decades was a 4-bit processor. And then came the 8-bit, 16-bit, 32-bit processors that we were using. And then memory constraints from 32 bits. Now we live in a 64-bit world. If you remember a few years ago, there was this big discussion on all the computers who are moving from 32-bit to 64-bit systems. Well, the reason is because when you have 32-bit lines, you have 32 wires, can only address 2 raised to 32 times of memory, just capped at 4 GB, or not capped. If you do the math, 2 raised to 32, it comes out to 4 gigabytes of memory. That's the max limit. So every industry was urging the computer industry or computing industry to move from 32 to 64-bit processors, so you can address 2 raised to 64 times the memory. Okay, all computing devices nowadays are 64-bit. So if it's 64 bits of data and you're running it in parallel, you would have 64 wires coming out the back of your laptop. Okay, think about that. We used to have that. If you've ever seen older desktops or older laptops, I've actually seen laptops which have parallel ports in the back. If you count the number of pins in that parallel port, it would be 16 or even higher for 32. So there used to be serial ports and there used to be parallel ports on the back of our computers. Serial ports were used to connect to instruments. There was also another port called General Purpose Interface Bus, GPIB. Serial ports, again, used for communications. Older modems I still remember the sound of the modems connecting to the internet like more than 25 years ago. And those were all serial connected. And then you had printers and other peripherals that were using parallel ports to send data in and out. Okay. So when you have these mix of serial and parallel systems, you need an interface that would convert serial into parallel and parallel into serial. And we can do this by using such a system. This is a serial in and parallel out shift register. Okay. You can send the data input in a serial fashion. Meaning the bit gets sent over one single wire, and the output is taken collectively across these. And so output is now in parallel, all at the same time. Okay, all at the same time. The reason it's known as a shift register is evident from the connection. This is an array of D flip-flops, 4 D flip-flops, flip-flop 0 to flip-flop 3. The output of the first flip-flop, FF0, is fed as input to the next, which is FF1. So D0 is the first input, Q0 is the first output. The output of the first one is fed as input to the next. Output of the second one is fed as input to the third, and third goes to fourth. So Q0 and D1 are the same. Q1 and D2 are the same, and so on and so forth. This is a 4-bit counter. You can have 8 bits, 16 bits, 32 bits, 64 bit, right? But essentially the operation remains the same. Now, D0. Let's look at the clock. The clock keeps everything in sync. The clock is a positive edge triggered clock, meaning for every single clock cycle, the input that appears at the input signal that appears at each flip-flop is then sent to the output of that flip-flop, but only when the positive edge of the clock arrives. So I can explain the operation of this by using the timing diagram. In this timing diagram, you have the clock signal at the top, right? 4 pulses. You can see there are 4 positive triggers. Those are the ones that we need to keep in mind. Those are the only ones when the data shifts or moves to the output of the flip-flop. This is the original data that is being sent. 0, sorry, not 0. 1, 0, 1, 1. Okay, 1, 0, 1, 1. That's the data that's being sent. This is an ideal example, meaning the width of the data pulse is exactly the same as the width of one clock cycle. Okay. One clock cycle is basically one on and one off, right? One cycle. You can say on and off or off and on. Doesn't really matter. Either ways. But the point is, each flip-flop is only going to send the D input to the output Q when the positive edge trigger arrives. Okay. One other key thing to keep in mind. Our graph or our timing diagram is typically, it's a graph, right? So 0 is on the far left, and then future is as you go towards the right. T is 0, T is 1, T is 2, 3, 4, 5, 6, right? So 0 is when you begin your analysis, and then the rest positive is the future. In the circuit, the data is going in from the left. The data is going in like this. So if you're sending in 1011, your 1011 is being sent like this from the left. Okay. In the timing diagram, we read it as 1011 like this. In the circuit, if you're feeding it from the left, it will read the opposite. Does that make sense? You're sending in 1011 again. The data that you wish to send is here, 1011. If 1011 is going in, you first send 1, then you send 0, then you send 1, and then you send the last one. You're sending it serially. Make sense? If you wish to send in 1, 2, 3, 4, if you wish to send 1, 2, 3, 4, this is how we would send it. We would send 1 first, then 2, then 3, then 4. That's what it is. Okay. All right. So 1011. This data input is basically going to D0. Flip-flop 0. That is then fed as input to Q0. So Q0 is D1. Q0 and D1 are connected together. Then output Q0 is fed as input to D2. So Q1, D2, and that goes to Q2. And thus we receive Q3. Okay. Since we are sending it serially and then taking our output in parallel, our parallel output is counted as Q3, Q2, Q1, and Q0. Okay. Least significant bit would be on the left. And so our output in a parallel fashion would look like this: Q3, Q2, Q1, and Q0. That's how it should look. So it should look like this. Parallel 1011. All right. Any questions so far? Okay, let's look at the timing diagram then. Here the clock is 0, so nothing happens, right? Nothing happens. Data signal arrives. It's at 1, right? Here it's 1. D0, the input to the first flip-flop is 1, but the output is 0 because a positive edge of the clock has not yet arrived. Positive edge of the clock arrives, meaning there's a delay. This is the delay right there. Positive edge of the clock arrives, it is now sent to the output. And hence this arrow right here. The one that was available at the input is now sent to the output. So you have a 1 right here. And it will stay at 1, right? It stores that data in memory. It will stay at 1 until the next positive trigger arrives. It will not change value. It will stay at 1. So it's 1 here. It stays at 1 until the next positive edge arrives. Now the input has gone to 0. The input is 0 here and 0 here. The input is 0, but the output still stays at 1. Output does not change until the next positive edge arrives, When the next positive edge arrives, the input 0 is now sent to the output. So the output remains at 1, but then at this edge right here, output goes to 0. And then it stays at 0 until the next positive edge arrives. So even though the data has changed to 1, the output still remains at 0 because the next positive trigger has not yet arrived. Is everyone with me so far? Cascading effects. Okay, make sense? Okay. All right, so then next positive edge arrives, input is 1, and so output goes 1. And then data remains 1 all throughout. So even when the fourth and the final positive pulse arrives, output is still going to remain 1. After that, it does not matter. Right? We are only shown 4 clock pulses. Let's say we applied 4 pulses or 4 clock pulses and we turned it off. Now clock is 0. Okay. Does the output of the first flip-flop change? No, it stores in memory. So the output of the first flip-flop will remain 1 for infinity. It doesn't matter what happens at the input. There is no clock that arrives it to activate the output. Okay, so the output is going to remain high as long as power is supplied to the circuit. Hence memory. Okay. Does that make sense to everyone? Let me know if you have any questions. Good. Okay, so that was flip-flop 0. Let's look at what happens to the next one. Flip-flop 0, the output of flip-flop 0, Q0 is fed as input to flip-flop 1. So Q0 is the same as D1. Right? You look at the circuit, Q0 is the same as D1, Q1 is the same as D2, and Q2 is the same as D3. So those timing diagrams are not shown here, but they're effectively the same, D1, D2, and D3. So D1 stays at 0, and it stays at 0 because Q0 was 0. So if Q0 is 0, then D1 will remain 0 because there is no positive edge that arrives when when Q0 goes to 1. So the output D0, which is right here, this one, sorry, not output, the data input that goes into flip-flop 0 causes Q0 to go 0, 0 and 1, 1 for this first rectangular pulse, right? And then let me draw the first rectangular pulse here, and the second one here, third here, and the fourth here, okay? When the first rectangular pulse arrives, all 4 flip-flops are 0, 0, 0, 0, right? That state is 0, 0, 0. So when the first one arrives, if Q0 is 0, then Q1 will also be 0. It's not going to change, right? It's only when the second one arrives that Q0 is 1, and hence that 1 now moves down the line, and Q1 also goes high. And if you look at the timing diagram, we can see that the data that was present in the first flip-flop is now shifted down to the second one. When you look at the third one, that data shifted further down the line. Cascading effects because of the serial connection, and hence the name shift register. For every clock cycle, the data shifts in a serial fashion. It cascades down the line because the output of the first flip-flop is connected as input to the next. So again, output of each flip-flop is connected to the next flip-flop in line. Okay. And so we get a cascading or a shifting effect. And so the data keeps on moving down the line. You get the same pattern repeating itself. Okay. We can do this for 8, 16, 32 clock cycles. We're only showing 4 clock cycles here. So 1, 2, 3, 4, because you're only transferring 4 bits of data. Okay, we're only transferring 4 bits of data. So you're only showing 4 cycles for this example. But you can draw the timing diagram for 8 clock cycles and 16 clock cycles. And we'll see that the exact same pattern will get transferred down the line. And you'll get the exact same pattern available at Q3, Q2, and Q1. Okay. We're just not showing those at this point. And now the data is fed in. When you want to obtain output, we are simply reading Q3 to Q0. So we read this fashion from Q3 to Q0. What do you see? You have a 1 here, and you're reading this. In the 4th clock pulse, we have a 1, then we have a 0, then we have a 1, and then we have a 1. And what did we send in? We sent in 1011. We sent in 1011 in a serial fashion, but we collectively take the output all at one instant across Q3 to Q0. We get the exact same data, 1011. And hence serial in, parallel out. All right, let's take a pause. Let me know if you have questions. Yes. So the clock keeps everything in sync. So the clock is the main signal or the main input signal that keeps everything in sync. Otherwise, none of our circuits would actually work. We would not know, which flip-flop is going to be active at any given point in time. All right, so that's serial in, parallel out shift register. The next slide shows us the opposite, which is parallel in and serial out. Okay, parallel in and serial out. And in this case, let's show here. Okay, all of the data is going in a parallel fashion all at once. The output is now taken in a serial fashion. However, it does not preclude a serial input. It's the same circuit. So we can send in the data in a serial fashion and obtain it at the output in a serial fashion. So we have multiple options. Sending in data all at once. Not all at once. Sending in data in a serial fashion, bit by bit, or you can send it all at once in a parallel fashion and then obtaining the output in serial fashion. Or you can connect the outputs directly here and you can get the output in a parallel fashion. So this circuit comprises of everything, right? All options. In fact, in the lab, if you see, you constructed a counter circuit. In the counter circuit, you connected the data in a serial fashion, but then the outputs were connected to LEDs, so the output is in a parallel fashion. Okay, so if you did lab 6 already, that's something that you already encountered in the lab. All right, let's see. So let's break the circuit down. What do we have here? All of the parallel data inputs are fed via an AND gate. Okay. They are fed into the circuit via an array of AND gates. And one input of each gate is connected together, known as enable. Enable circuit. All right. Then at the bottom, we have clock. That's a standard. And then clear is also standard. Clock keeps everything in sync. The clear, of course, clears out the register of memory and it just sets everything to 0. Right? Clear sets everything to 0. Preset sets everything to 1. The reason the clear is set to be asynchronous is because it's not connected to any clock signal. If you want to reset our controller boards or our chips or something like that, we press a reset button. That's what this is doing. It clears everything out from memory and it sets everything to 0. So that's why it says asynchronous. All right. Output of each is fed as input to the next. So we have serial connections right here. And the AND gates are all connected to the preset button of each D flip-flop. Okay. The AND gate output is connected to the preset button, which is right there. When the preset goes high, the output of each flip-flop is set to 1. Let's look at the AND gate. For an AND gate, what happens when one of the input is equal to 0? What's the output? 0, right? So doesn't matter what you supply as input to the AND gate. If one input is 0, the output's always going to be 0. So if the enable pin is logic 0, then the outputs of all gates are 0. Preset is equal to 0. It does not do anything to the flip-flop. The output is stored in memory. If the output is 0, it'll stay at 0. If the output is 1, it'll stay at 1. So when enable is equal to 0, the AND gate output is equal to 0. What if the enable pin is high? Meaning enable is equal to 1. The AND gate output would be equal to whatever data inputs you provide. If your data input is 0, the AND gate output is 0. If your data input is 1, your AND gate output is equal to 1. So using this connection permits us to send our output through only when the enable pin is high. And so AND gate output would be equal to the parallel data input. Okay. So let's say, for instance, we wanted to send the input that we used in the previous example, 1011, right? So you're sending 1011, and the enable pin is high. So the enable pin is high, it's going to send 1011. And if that's the case, initially, of course, we think, I mean, not we think, we set everything to be 0000. Now we are sending an input. We're sending an input 1011. So that goes to the AND gate. The AND gate output is also now 1011. That goes to the preset button. If the preset input is 1011, the output of the first one goes 1011. And now with each successive clock cycle, the data is going to shift out, right? First clock cycle, that one shifts out, the 0 moves down the line. Next clock cycle, the 0 shifts out, the third bit one moves down the line. And the fourth clock cycle, one more shift down the line. And so now you send the inputs parallelly into the circuit, and then one step at a time or one clock cycle at a time, it's shifting out. So parallel in and serial out. Let's take a pause while you think over that. Let me know if you have any questions. Do the steps make sense? Right? And all combinations possible just simply means you can send serial in, serial out, parallel in, parallel out. Excuse me. And then serial in, parallel out, and parallel in, serial out. Okay, so the circuit can do all of it. Obviously, we don't see parallel connections anymore. Not outside of the system. Inside the system, yes. Not outside as an external interface. You'd have a 64 wire connection coming out, right? So have you ever used it? Parallel connections, serial connections? No, you use serial connections every day. Universal Serial Bus, USB. That's where it comes from. So USB connection is a serial connection. And the reason it's called universal is because now it's used for pretty much, every, well, even when it was invented or, they came up with the universal bus, they meant to use it as a standard communication with all external peripherals. So all printers, all accessories connected to a computer or computing device would now use that universal bus as common. So hence universal serial bus. A USB connection has 4 wires, plus 5 volts, 0 volts. So power supply lines, and then 2 data pins. I mean, D plus and D minus, data plus and data minus to complete the connection. If you have a cable that only has the power lines, you can only use the cable for charging. You can't use it for data transfer. And then depending on the manufacturer, some cables are able to convey data using the D plus and the D minus lines. So you can connect your phone or your tablets to a computer and use them as a external drive. But that's where it comes from, USB. There was a while where there were several printers. We used to come with a big parallel port and a USB port together. That was a time of transition. Now, of course, they only come with a USB or just wireless. Right? Okay, so that is the end of chapter 4. Chapter 5 is pretty much an overview of microcontrollers, microprocessors, basically computing systems. Okay. So, as I said, we were far ahead of schedule. What I wanted to do in the 15 minutes was talk a bit about the labs. So we had, where is this one? Yeah. Lab 6, 7, 8. That's 6. Oh. And that is 7. And that would be 8. Actually, I have all of them here. All right, so 6 is basically we are taking different gates, creating a flip-flop, and then there is a separate IC which actually has a flip-flop, and we'll use that flip-flop to create a counter. Okay. So the first one, I believe, is using a NAND gate. So this NAND chip has 4 gates. And the first circuit was using this NAND chip to create a RS flip-flop right there. By the way, I always repeat this all the time. The lab write-ups have excellent background sections. So if you have not been reading it, please read it because it explains what the circuit does in quite some, it's brief explanation, but it explains everything in detail. So again, we use the NAND gates to create your flip-flop, and then use the, so that's procedure 1. And then procedure 2 is creating a 4-bit counter, the one that we just talked about. Output of each is fed as clock to the next one. That's the ripple counter that we saw last class, right? When you build this circuit in the lab, you're going to use 2 chips, 74107 and a second one, 107. So that's the first, and that's the second. Okay. The pin out configurations that you see here, pin numbers 1, 12, 4, 7, 13, 3, 2, all of that remains the same. My suggestion to students always is divide the circuit in half, like right down the middle, right here. Okay. And create these 2 with 2 JK flip-flops inside each chip. Create them separately because they're the same pinouts. It gets confusing. Once you create these separately, meaning the first one separately and the second one separately, then take a single piece of wire and connect pin number 5 of the first one to pin number 12 of the second one. Okay, so you split the circuit down in the middle right here. Oh, actually, you know what? Let me. Okay, so here's the middle right here. Okay, to the left is chip number 1, to the right is chip number 2. Both are the exact same ones. The pinout is exactly the same. The connection is also exactly the same. What we are doing here is the forbidden state of RS. In RS flip-flop, if you have R as 1 and S as 1, we can't predict the output, right? In a JK flip-flop, we can. In a JK flip-flop, if you connect J and K inputs to 1, it works as a toggle flip-flop. It toggles the output. And that's what we're doing here. We connect J input, which is 1, and K input, which is number 4, right there, 1 and 4, and you connect them both to +5 volts. So the output is just toggling. So the first JK flip-flop is 1 and 4. The second one is 8 and 11. Okay, so pin numbers 1, 4, 8, and 11 are connected to +5 volts. And you do the same thing for the second chip. Okay, do the same thing with the second chip. And then once you're done with both, then you simply take one wire, connect pin number 5 of the first one to pin number 12 of the second one. It's a 4-bit counter. And you'll have LEDs. The LEDs are connected to Q0 output. So the cathode is connected to Q0. When Q goes to 1, Q0 goes to 0. Right? Since Q is fed as clock to the second one, we don't want to interfere with that. So we connect the output to Q0. So when Q goes to 1, Q0 should turn on the LED. But because it's 0, we connect the LED cathode to the output of the chip and not the anode. So the anode is held at +5 volts. When the output Q0 is 1, meaning Q is at 0, the LED should be off. So if Q0 goes 1, cathode is also 1, and anode is also 1, the LED turns off. If we wish to connect the LED to the Q output, we would connect the anode to the Q output. and not the cathode. It would flip. That's why dual outputs are very useful. That's why Q and Q naught outputs are very useful. Okay. Anyway, so that's the 4-bit asynchronous counter. Once you have this, you'll see the LEDs light up. You'll see the LEDs go 0, 0, 0, meaning they're all off. And go 0, 0, 0, 1. One LED turns on. For those of you who finished the lab, were you able to do it successfully? Lab 6. Good. Almost. Glitches in there. Okay. Okay. That's still good. At the end of lab 6, it will tell you, do not dismantle the circuit. Keep it as it is. Because what we are doing in lab 7 is, in lab 7, you'll take the output of this counter circuit. You're going to use a decimal digit display. And the decimal digit display is known as a 7-segment display. And that's lab number 7. In lab number 7, we use something known as a 7-segment display. These were very popular. These still are popular in many areas. So if you have a LCD display, if you look at each individual digit, you will see a 7-segment display. These are 7 segments in there. These are all 7 LEDs. Okay, so these are 7 LEDs plus an 8th one to show the decimal point. Okay, but 7 of these, A through G, A, B, C, D, E, F, G, each one of them is an LED. Okay, if you tie all the anodes of the LEDs together and connect it to +5 volts, then you can control the signals going into the cathodes. That would be known as a common anode display. If you connect all cathodes of the LEDs together and connect it to ground, that would be known as a common common cathode display. So you can have common anode or common cathode displays. So it's nothing but an LED. The input to each LED is provided by this decoder. This decoder is known as a BCD to 7-segment decoder. BCD is a binary coded decimal system. Okay, binary coded decimal. And there's a encoder that we can use. So binary coded decimal means you have your 4-bit display, right? How many digits in decimal? 10, 0 to 9. If you want to go up to or count up to 9, you need a 4-bit counter, right? You need a 4-bit counter. So 4-bit counter goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 8 and 9 require 4 bits. If you're counting up to 8, you only need 8 possible states. So if you want decimal, you need 4 bits. If you did 4 bits, it goes from 0, 0, 0, 0 to 1, 1, 1, 1. A BCD, binary coded decimal system, will take the 10th position and reset to 0 after the 10th position. So it counts from 0, goes to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are still 6 possible states left, but in a BCD system, the count resets to 0. And that's what a BCD is. So binary coded decimal BCD would reset the count to 0 after it counts through 10 states. And then a BCD to 7-segment decoder is simply used to light up this LED. So lab 6 at the end, once you have the 4 LEDs working, going from 0 to 15, you'll build this, and then you'll be able to see the count in the 7-segment display go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, reset to 0, and begin counting again. And that's what you'll be able to see on this. Okay. That's lab number 7. And then lab number 8. Ooh, that's a beauty. This is the circuit for lab number 8. This has nothing to do with lab 6 or 7. Okay, lab 8. The first time I did this was about 5 years ago. So when I created the circuit, it looked so beautiful. Something about circuits and breadboards is very aesthetically appealing to me. So it was looked really beautiful, and I kept it as it is for all these years. And every single time I teach 361, I bring it in the first day of lab class and I show it to students. And this is what we're going to build in lab 8. Okay. And the circuit looks like this on the breadboard. Oh, this is not my version. This was done before I came. But mine looks a little similar to this one. Okay. This looks much cleaner because you're using smaller wires that can plug directly flat onto the surface of the breadboard. What you're doing here is, let me explain this in brief. I have a few minutes left. We did the analog comparator. Remember in lab number 5, we did an analog comparator where you had a comparator, LM311, and you set one of the inputs using a potentiometer, right? And you set it to, let's say, in the middle of the potentiometer. That means half the resistance. Between 0 and 5, you get 2.5 volts. So 2.5 volts is set as one input, and then you had a clock counter or sine wave that was cycling through 0 and 5 volts, right? Analog signal. Every time the comparator input went above 5 volts or above 2.5 volts, the output of the comparator went to plus 5 volts. Anytime the sine wave went below 2.5 volts, it turned off. So you had a pulse that appeared. Output of the comparator was like a rectangular pulse. If you turn the dial of the potentiometer, the on time of that pulse would increase. If you lowered the voltage, the off time would increase. Okay. On time and off time. That's a width of the pulse. If you increase or decrease the width of the pulse, it's said that you're modulating the pulse width. Hence the name of the technique, pulse width modulation. And you can use pulse width modulation, PWM, to turn on or turn off the transistor. So the output, you see this transistor that's used as a motor driver. So when you change the width of the pulse, the amount of time the transistor is on or off changes. And that changes how much voltage is being sent to the motor, or how much it's being turned on and off. Okay. And so the speed of the motor now changes. And that's pulse width modulation. So we did the analog comparator. This one right here, the long rectangular chip, the 7485. The 7485 is a digital comparator. It compares two 4-bit digital inputs, A and B. The B input that you see is manually set either to plus 5 volts or to 0 volts. And it's set through this DIP switch. Dual inline pin has 4 switches in one. It's a small black switch with a white slider on it in your lab kits. So you set that switch. If it's off, your inputs are 0, connected to ground, right? Directly connected to ground right here, the 330 ohms. So B input is all 0, 0, 0. When you turn the switch on, it's now connected to plus 5 volts. Does that make sense to everyone? So now you're changing the input. So you set the input B, and then here is a free range counter. This circuit right here is a counter. You apply a clock pulse to it, and it's just counting. So the 4 outputs that are going into the input A, it's 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, and so on and so forth. So it's continuously counting. Depending on the set input, if you set your B input to 0, 0, 1, 1, if your counter is below 0, 0, 1, 1, output is turned off. When it counts up, output is on. When the output is on, the transistor is on, your motor is going to spin. When the counter stands below, motor turns off, or the speed turns off. You generate a nice staircase waveform, and then you're going to capture that output, and that's the waveform, but that's how you're going to vary the speed of the motor. And that's basically how the circuit operates. So there's a nice picture and image of the circuit that was built the first time. You can try and set it out as it is. These are 3D printed parts. There's a motor holder and there's a propeller kind of fan blade. These are both printed, 3D printed. So if you send in the request to Mustang 60, if you're red dot certified over there, if not, there's a great time to do so. There are 3D printers in there. You can go in and print your own parts. Okay. I would assume you are like juniors and seniors, mechanical engineers. You would have stepped foot in Mustang 60 at some point. So get your red certificate or red dots. I don't know what they call that, red dot certification, and you can go in and print the motor holder yourselves, or you send in a request. All right, we'll end class here today. We'll see you on Monday. Monday is a quiz, a big quiz. I will post the announcement in just a few hours. Okay. Well, big quiz in the sense that we've been doing 20-minute quizzes, so might be 30 minutes, but I'll give some extra time. All right.